Hello and welcome to this lesson on exponential functions. Now, those of you who are being taught by me will know, because it's pretty standard now, that those are the questions from the Cambridge Essentials textbook series that I would very much like you to do. This will give you a great cross-section of questions to sort of practice the skills we're about to learn. Those of you who are watching Internet Land, hi, welcome. Tell your friends about me. And that's slightly weird and slightly needy, but I really could do with the subscribers. Why not subscribe yourself if you've just found my channel? Alternatively, go to MaffsGuru, maffsguru.com, where hopefully you'll find everything that you need to sort of teach you all the stuff that you may not currently understand. Okay, so as is normal, here is a recap. In previous exercises, we've been looking at a number of functions which are used throughout maths methods. And again, if you're at an internet land and don't know what maths methods is, it's the equivalent of A-levels and high school maths. We have looked at sine, cosine, and tangent graphs, hyperbolas, trunci, square roots, and cubics, to name but a few. And again, these are not an exhaustive list. Please don't think that if you learn all of those, that's it. You are learning a skill set. You are learning how to apply maths to a lot of different things. So there might be stuff on the exam that you're not initially aware of, but you can still apply your understanding. With all of those, and if anyone thinks anything about this course so far, and we've been doing this for now nearly 2 terms, it's all seemingly about dilations, reflections, and translations. The order of transformations is really, really important. Again, I keep going over this, but if you're new to this video series, maybe you won't have heard it. Where there is no order given to transformations, you must consider them by using Dr. T. Dr. T, yes, not Mr. T from the A-Team, but Dr. T is dilations, reflections, and translations. In fact, that was the order you've got here. So Dr. T just comes from those first letters. This module, all right, when we're dealing with things very much in modules, we don't tend to go through the course chapter by chapter, is looking at 2 further families of functions: exponential graphs and logarithmic graphs. Oh, logs. Go and say that to your mum and dad, and they will start to tremble undoubtedly. I mean, certainly if they were my mum and dad's age, they'll be sitting there going, oh, log tables, what did that all talk about? But anyway, as is normal with all graphs, an understanding of what the base graph looks like. And again, I keep saying this once. I think the trick to methods is knowing what the base graph looks like. If you know what the original non-transformed function looks like, the rest of life should become much simpler, as long as you know how to transform graphs. All right, so at this moment in time, we're going to deal with exponential functions. Now, I don't know about you, but I would love to be a millionaire by the time I retire. Time kangaroo down sport. This was entirely possible had I do the following. And actually, I'm going to give you my advice. If you want to become a millionaire, knock yourself out. How do you do it? Find a bank account that will pay a fixed interest of approximately 7% per annum. And if you don't know what per annum is, go out there and get a bank account. Deposit about $3,000 per year for about the first 10 years. Now, that might seem a lot. If you save and don't have all your smashed avo, then maybe you could do it. Then, basically, leave it alone. Don't touch it. Let it grow. So put it in there, 10 years, just forget about the bank account. When you want to buy a new car, don't dip into the savings. When you want to buy a house, don't dip into the savings. Just leave it. What actually happens is, using compound interest, the money you have actually grows really slowly at first, but then it starts to grow quicker and quicker and quicker and quicker and quicker. Now, why? Because you're getting interest on your interest. So each year you're earning interest, but then you're earning interest on the interest. And by this idea of compound interest, which you may have met previously in maths, you tend to find that money, after about 60 years, will have topped over $1 million. That is pretty funky. Now, God, I wish I'd done that. I'd have been a millionaire in about 20 years' time. Sadly, as it says here, I didn't do it. But this curve, this general idea here, is called exponential growth. Ooh, exponential growth. Exponential. And as I say, that's what we're going to be dealing with. So let's go to this base function. Now, a base function of an exponential has the formula y equals a to the x. And it basically says that a is in all real numbers, or all positive real numbers, but not 1. Oh, hello, close that little squiggly thing here. Now, obviously, if you put a equals 1, then 1 to the power of x is always going to be 1, which is a straight line. So you're not going to get that exponential growth. But here are 3 examples of exponential graphs where I've made a 2, 3, and 4. So this one here is y equals 2 to the power of x. This one here is 3 to the power of x, and this one here is 4 to the power of x. Now what you notice is they all have identical shapes. Identical shapes. Similar shapes. All of them go through the coordinate position 0, 1. Now why would that be true? Well, if you look at the graphs of 2 to the x, 3 to the x, and 4 to the x, when x equals 0, you get 2 to the 0, 3 to the 0, and 4 to the 0, and as I'm sure everyone in here knows, anything to the power of 0 is in fact 1. Yes, indeedy. Then we get this coordinate here. Now, I've given deliberately 1, 2, 1, 3, and 1, 4. Why? Because I said, well, look what happens when x equals 1. In the same way as you have here, you'd have 2 to the power of 1, 3 to the power of 1, and 4 to the power of, not 4 to the power of 4. 4 to the power of 1, and anything to the power of 1 is in fact itself. So that one key point is really, really helpful. Something that might not be immediately apparent is in fact that there is an asymptote at y equals 0. Interesting. All right, so that would suggest the maximal domain is from minus infinity to infinity. You can put any value you like into any of these exponential graphs, and you'll get a value out. But the range is R+. It does not include 0 because of this asymptote here. And we'll explain a little bit more later on why there is an asymptote. So they are my base functions. There are my graphs. Now, going back to the idea that we have y equals a to the power of x. When the value of a is greater than 1, then the graph all looks the same. It's all, as you see, this type of shape. Goes through 0, 1. And it will have some sort of coordinate. Well, of course it'll have some sort of coordinate. God, what am I doing today? Stating the obvious? Beautiful. Beautiful, 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 beautiful. But when the value of a is between 0 and 1, but obviously not including, the graphs will always have the shape shown below. So in this situation, rather than going up, it's actually reflected in the line x equals 0. Same situation, if you notice, it's still going through the point 0, 1, but in this situation, when I have my 1 position, when I have 1 in there, then I get 0.5 out. Now why? In this case, this graph would be y is equal to a half to the power of x. Now when we have a half to the power of 0, it's still 1, so that's my coordinate position there. When we have half to the power of 1, it's obviously a half, so that explains my 1, 0. When we have a half to the power of 2, and I'm going to put it all in brackets, if you think that becomes 1 over 4, and when we have 1 half to the power of 3, we get 1 over 8, and when we have 1 half to the power of 4, we have 1 over 16, and what you notice is as the x values get bigger, then our y values get quite quickly smaller and smaller and smaller, exponentially as it turns out. So that sort of explains why the graph goes that way around. Really, really important to notice. Going back to stuff we did way, way, way earlier in a previous video that dealt with the basics of transformations, sometimes it's always really helpful to learn the shortcuts about how to go from a base function into a transformed function. Again, there are lots of ways of doing this, by algebra, by all sorts of different stuff, but maybe the quickest way is learning these dilations, reflections, and translation shortcuts, and what to do with the original function. So a dilation from the x-axis says to replace y with y on b. I'm going to rub out this just in case anyone wants to print it off. A dilation from the y-axis replaces x with x on b, where the b is the dilation of the, and so it goes on. Again, there's a great video on this previously if you don't remember it. But these shortcuts can actually help us also not only create a new function, but unpack transformations of exponential functions. So let's look at very quickly the idea of translating the graph of y equals a to the x. Here's a function y equals 3, x minus 1 plus 1. If you want to be good at methods, if you want to be good at the exam, and really you should have been doing this in sort of methods 1 and 2, but we need to start looking at, well, looking at a function, what's my base function? Well, it's obviously going to be y equals 3 to the x. And I say it's obviously going to be, well, hopefully you can see that it's 3 to the x. This minus 1 seemingly will do something, and this plus 1 will do something. Well, it turns out that those are both translations. because this is by my x or inside the x or by the x or blah, 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 then it actually is a horizontal translation in the direction opposite to what you're expecting. So first things first, it's going to move that way 1 unit. And this N1 here is a y translation. So it becomes y, so we should move 1 unit up. If you're interested, there we go. That's the information about saying why is the function so, because we've actually used the shortcuts. We notice that a translation horizontally says to replace x with x minus h, where h is the number of units translated. So what do we notice? We've had y equals 3 to the power of x. That's been replaced with 3x to the minus 1, and so it must be translated 1 unit. Likewise, we've replaced y with y minus k, where the k is the number of units translated. So where we had y equals 3x minus 1, we've now replaced that with y minus 1 is 3x minus 1, which gives me y equals 3x minus 1 plus 1. So there's my equation. I'm just using those shortcuts to help me. Having now got the idea of how it's been translated, drawing the graph is just awesome. Remember to always make sure you label x-axis, y-axis, or vice versa, as I've just said, asymptote. All right, so that's the value of y equals 1. That asymptote is critically important. Label any axis intercepts, and then I always label 1 extra point, just so the examiner knows. And it made sense that I was going to have the point 1, 1. I looked at the point 1, 1, and worked out, well, what's going to happen when I move this? Well, first things first, we have the graph of y equals 3 to the power of x, which means that its original point was actually 1, 3. Because when x equals 1, y becomes equal to 3. Then what have we done? We've moved it that way, 1 unit, so my x value becomes 2, 3, and I've moved it 1 unit up, so it becomes 2, 4. And there, ladies and gentlemen, is explaining why it becomes 2, 4. Those translations, let's look at reflecting the graph of y equals a to the x. Sketch the graph and find the range. Oh, we didn't find the range for the previous graph, but in this situation, because it said find the range is going to be 1 to infinity. Why? Range means the possible y values. So if we look at what our lowest y value is, it's 1, but not including 1 because of that asymptote. And it can actually go up to infinity and beyond. Right, that's enough of that. Reflecting the graph of y equals x. And again, so sketch the graph and find the range for y equals minus 2x. Nice, easy example. Again, what is the base graph? As I've stated here, it's got to be y equals 2 to the power of x. We're dealing with exponentials. We like what we see there as y equals 2 to the x. We notice that y has been replaced with minus y, so it's got to be a reflection in the x-axis. A reflection in the x-axis, our original graph, if you remember, would do this, which would cross through at 0, 1, and it would have a point at 1, 2. And so what we notice is, yes, ladies and gentlemen, it swaps to 0, minus 1. And the point 1, 2 becomes 1 minus 2. What is my range? Well, in this situation, if it's been flipped, it's just r minus. Again, make sure you label all of your x's, y, x, and your asymptote in this situation would have the equation y. Whoa, what happened there? Y equals 0. Yeah, all right, happy with that? Reflecting is lovely. Last one, sketch a graph of this function and demonstrate its range. So this is a second type of function. Base graph in this situation is y equals 5 to the x, which would mean that normally it would go through 0, 1, and my point would be at 1, 5. Notice how I draw these little sketches. It took all of about 4 seconds, but if that was the difference between getting me, this and 100 marks, I think I know what I'd actually be doing, drawing these quick sketches. Don't try and do stuff in your head. Right, what have we done? Well, we have replaced x with minus x, and so in that situation, it's a reflection in the y-axis. And there we go, ladies and gentlemen, a reflection in the y-axis. My point 0, 1 stays the same. My asymptote is still at y equals 0, and this is the x-axis. And the y-axis, I've labeled my crossing point, and 1, 5 goes to minus 1, 5. And so, smiley face, nice and easy. My range in this situation is, once again, r plus, or if I wanted to, I could write 0 to infinity. Moving apace, dilating the graph of y equals a to x. Now, dilating the graph is awesome, but it's a trick, and it's one that's used in the exams all of the time. Notice how it's written. Please, please, please do not think that y equals 2 times 4 to the power of x is 8 to the power of x. My heart breaks a little time every time I see that. It's not the same. Barry's trying to confuse you. This, the second I look at it in an exam situation, I'd be like, Barry, you're at it again. Thanks very much. I know that's an exponential. So I would be drawing a very quick exponential. I'd know that was 0, 1 because they all go through that. My base graph is 4 to the power of x. So that's going to be 1, and that's going to be 1, 4. Right. So if that's my base graph, what does this 2 do? Well, multiply by 2. Yep, it just means that I'm actually going to dilate 2 away from the x-axis. So there's my base graph. Yep, thank you very much. We've replaced y using these shortcuts from previous in the video. Y has been replaced with y over 2. Hence, it means there's been a dilation away from the x-axis. Well, using my base graph, I now know that all of my values are going to be doubled, barring this one. Obviously, it's still going to go through. That's not true. All of my values are going to be doubled, including this crossing point, because it's changing the y values. So rather than going through 0, 1, it now goes through 0, 2. And rather than going 1, 4, it goes through 1, 8. Once again, making sure that we make our examiners happy. There is y, there is x. My asymptote has the equation y equals 0. And I think that's probably got all of the marks that I should need in an exam. Finally, sketch the graph and find the range of y equals 3 to the power of 2x. Base graph, 3 to the x, yep. So again, 3 to the x, what is this going to do? We would normally go through 0, 1. We would go through 1, what would that be? 1, 3? Yep. So, what does this 2x mean? Well, again, it's the one that sort of fudges and tricks people a little bit. In this situation, if we go to the shortcut, we actually notice that 2x can be achieved by doing x divided by 1/2. Hence, the dilation is 1/2 away from the y-axis. If you're not sure why, go back and review transformations, right? I can't, this lesson's already 17 minutes long. I'm so sorry, I can't go back and do more and more and more. But the point of it is that 2x basically means a factor of 1/2 away from the y-axis. Now, that suggests that in this situation, that crossing point's not going to change. We're dilating the x, we're changing the x values. They're the ones that are actually going to change. Because it's away or further to the y-axis or closest to the y-axis. So the y values don't change, it's the x values that actually halve. So as you can see, that 0, 1 stays the same, but that now becomes 1/2, 3. There is 1/2, 3. Labeling my graph y, x, and my asymptote y equals 0, and I'm pretty much done. Now we can use all of those to combine transformations, and that's pretty much where this lesson finishes. This is a pretty tricky transformation, but look at unpacking it and looking for, what is it? We're looking for dilations, reflections, and translations. So do we see any dilations? Well, dilations are the form y equals a times a to the power of x. So is there anything timesing this thing? No, not at all. So that's good. So there are actually no dilations. Are there any reflections? Oh, y should go. There's a reflection seemingly there. And are there any translations? Yes, because that has an x minus 2 and that has a minus 3. So what is my base graph? Well, my base graph is y equals 9 to the power of x. Very quick sketch. Goes through 0, 1. 1, 9. So that's my base sketch. So what do I do now? I'm reflecting. So that minus sign tells me to reflect in the x-axis. So let's just not draw that one there. Let's draw this one here. So now my graph is going to do something like this. So it's going to be 0, minus 1. And this point here is going to be 1, minus 9. So that's my reflection done. Then I've got my translations. So that minus 2 means I'm going to move my whole graph 2 units that way. And that minus 3 means I'm going to move my whole graph down 3 places. So I can now say automatically that, 1, minus 9 is going to become 3, because I'm adding 2 onto that. And taking another 3 away, 3, minus 12. There we go, that point there, thankfully, is 3, minus 12, which for some reason I didn't label on this graph. My asymptote stays the same. No, it doesn't. My asymptote in this graph is actually drawn incorrectly. That's silly. My asymptote, if you now remember, awkward, is actually here. So ignore that one there. Y is equal to -3 is my asymptote. There is my x-axis. There is my y-axis. My intercept is labeled. Now, how do I find my intercept? Well, in this situation, while I can find this coordinate 3 minus 12 really easily, I'm not necessarily sure how to work this one out other than using algebra. Now, what do we know at this point here for the intercepts? We know the x value is 0. So if I had y was equal to -9, x to the power of -2 minus 3, I'm pretty sure that was my function, just reviewing. Yeah, I put x equals 0 in. So y gives me -9 to the power of -2 minus 3. And using my CAS calculator, I can work that out. Now, because this lesson's already 21 minutes long, I'm going to leave it there. But exponential graphs are awesome. These are base functions that you need to know, and exams use them left, right, and center. Now, another lesson coming up slightly later on is actually on the letter E, which is fabulous graphs, right? Still an exponential function, but I'm going to leave it here. Thanks very much for taking the time to join me. If you're new, why not subscribe? Otherwise, I look forward to seeing you next time. Hey guys, if you've enjoyed watching this video, why not tune in and subscribe to get updates of when I do other videos. Alternatively, click this video that's coming up now, or just zip on over to MaffsGuru.com, MaffsGuru.com, where you can actually access all the videos in a nice, easy to use way.